Today, let's talk a little bit about quantum computing. There are three main topics we'll discuss: superposition, classical computing, and quantum. Let's get started with superposition. First, we have to understand what a wave is. Waves have lots of properties such as amplitude, frequency, and wavelength. But the important thing for us to know is that if the top part of a wave, the crest, meets the bottom part of a different wave, the trough, then the waves cancel each other out. On the other hand, if two crests or two troughs meet each other, then one larger wave is formed. Now we have to understand Young's experiment, also known as the double slit experiment. As you can see, there is one wave that goes through two slits. When the wave touches the slit, it diffracts into two separate waves. Then those two waves interfere with each other. That is, the crests touch the crests, and the crests touch the troughs, and the troughs touch the troughs. That makes an alternating band of patterns on the opposite screen. That's why you can see dark, light, dark, light. So what do you think would happen if instead of a wave, we used particles, one by one, randomly going through each of the slits? You would probably expect these two bands. However, if this experiment is done at a small scale, say with electrons or photons, then something unexpected occurs. The interference pattern is back. This means that each individual particle, which goes through one slit or the other, is somehow acting as a wave. This can only happen if each particle is actually going through both slits and neither slit at the same time. That means it exists in multiple states at once. It exists in superposition.
The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other.
Now let's move on to classical computing. Firstly, in classical computers, we have little pieces of information called bits. These bits have values of either 0 or 1, and depending on the value, it represents a different piece of information. We can combine lots of bits together to create bytes, and then kilobytes, and megabytes, and gigabytes. The Turing Machine is a basic method of classical computing. It has a head which reads each bit, figuring out whether it's a 0 or a 1. By processing lots of these bits, our computers perform tasks such as sending email and playing videos. Now let's go into the small scale and explore quantum computing. Instead of bits, quantum computers have qubits. Remember what we learned about superposition? Well, the values of qubits are in a superposition of both 0 and 1, so it has both values. However, when we measure a qubit's value, it becomes 0 or 1. This will be explained momentarily. Because qubits can store a 0 and a 1 at the same time, quantum computers can store more information than classical computers can. Here we see 3 bits. They all only hold one value at a time, but a qubit can have one of 2 values. So while a set of bits has only one possible combination of values, a set of qubits has several. However, there is one big problem with quantum computing. Once we retrieve a piece of information, the qubits all get assigned a definite value. So instead of having 0 and 1, each qubit becomes either 0 or 1, and suddenly all the other possible values are lost. This is called decoherence and is a big problem.
When they observed, the electron went back to behaving like a little marble. It produced a pattern of 2 bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one.
Dr. Supriyo Bandyopadhyay is the quantum informatics teacher at the Virginia Commonwealth University. To summarize what he says here, this problem of decoherence is the largest issue with quantum computing. It is possible to recover information that has been lost by measuring a qubit's state, but it requires an impractical amount of computing power. But never fear, there is progress being made towards practical quantum computers. Dr. John Dell, quantum physics teacher at Thomas Jefferson, believes that quantum computers with practical decoherence methods will exist in the lifetimes of current high school students. With quantum computers, computations that would take classical computers several years to complete will be done in a matter of seconds. These incredibly powerful computing devices are only one of the many applications of the amazing world of quantum physics. Thank you for watching.